Have you ever wondered why some things are normally seen as a certain phase, such as liquid water, nitrogen gas, or even grains of solid salt? What about why that salt dissolves in water? Today on Jason Explains, we will explore the forces between molecules that influence the state of matter, intermolecular forces. Before I go on, intermolecular forces are the forces that exist between molecules. These are not those bonds between atoms that you hear of. Those forces are called intramolecular forces as they exist within a molecule. Here, we will be learning about intermolecular forces involving ions, dipoles, and induced dipoles. You'll become familiar with these words as I go on. To begin, ions are atoms or molecules that have an overall electric charge due to loss or gain of electrons. One more term to know is electronegativity, or the tendency of an atom to attract bonding electrons. When two atoms with a big difference in electronegativity meet, the atom with a higher electronegativity takes electrons from the other atom, creating a positive and negative ion. By taking or losing those electrons, this is not technically an intermolecular force, as this interaction between these atoms basically created an ionic bond, which is an intramolecular force. Now, we go on to dipoles. These are molecules which a negatively charged area is separate from an area of positive charge. This happens when the atoms in a molecule don't have enough difference in electronegativity to take or receive electrons from the other atoms, but they still have a big enough difference to drag shared electrons closer to atom or atoms. This makes area or areas of a partial negative charge, as the negatively charged electrons are closer to that side of the molecule. Meanwhile, the areas that had electrons pulled farther from would have a partial positive charge, as electrons are farther from that side of a molecule. This makes the molecule polar, or have an uneven distribution of electrons and have partial charges on different sides of the molecule. Many factors can influence the strength of these charged areas. Mainly, the larger the electronegativity difference, the stronger the charge is. Another factor is bond length. The longer the bond, the stronger the charge in the regions. In a dipole-dipole relation, the negatively charged parts of the molecules attract the positively charged part of another molecule and vice versa. So, molecules are aligned to best fit the electric charges in the area. This force is stronger the more charged the regions are. Oh, I almost forgot. One factor in determining whether a dipole is formed is the molecule's shape. Even with these polar bonds, or bonds with uneven sharing, which I just explained, a molecule is not quite a dipole yet. In order for it to be a permanent dipole, it must also not have symmetry that cancels out the charge difference that was just made. So, water would be a dipole as its bent shape gives a definite area of partial positive charge where the hydrogens are, and a definite area of partial negative charge at the oxygen end. Meanwhile, carbon dioxide is not a permanent dipole, as even though the oxygens are partially negative, the linear arrangement of this molecule cancels out this charge formed. There is also a special type of dipole-dipole force, hydrogen bonds. This special type of dipole-dipole only occurs when hydrogen bonds, in our purposes, with nitrogen, oxygen, or fluorine, and is interacting with another nitrogen, oxygen, or fluorine. These three are very electronegative atoms and would pull the bonding pair with hydrogen closer than other atoms, making hydrogen have a very positive partial charge, meanwhile giving the other atom a very negative partial charge. The other atoms are also very small and would at least have one lone pair of electrons, giving a higher concentration of negative charge, as well as letting other hydrogens get close to the atom. Now, if you notice, water, with the formula of H2O, fits this description, and yes, it does form hydrogen bonds. This explains the relatively high boiling point of water compared to substances such as most alkanes. As the hydrogen bonds continuously forming and breaking in the water pull the molecules together stronger and take more energy to break. Here, I would like to go back to ions and combine that with what we just learned about water to explain ion dipole forces. When you pour salt into water, doesn't some of it dissolve? Well, this is because the polar molecules of water start splitting the salt into individual ions. Once this happens, the partial charges of the water molecules align to face the opposite charges in the ions surrounding the ion. This ion dipole force is mainly influenced by charge difference, or the greater the difference in charge, the stronger the interactions. This should also work for any other polar molecule, as the water would do the same to it as what it did with the salt which I just explained. At this point, you may be wondering, what about molecules that don't fit this? I swear, I've heard of things like liquid nitrogen. What forces are between those molecules? Well, these molecules of nitrogen, or N2, certainly aren't permanently polar with no difference in the electronegativity of the atoms within. Wait, did you just say permanently? Yes, I did. Nitrogen molecules have moments where they are polar. This is caused by the random movement of its electrons. Sometimes its electrons just happen to be concentrated on one side, meaning that that side would have a very slight negative charge, while the other side has a slight positive charge, making that molecule polar in that moment. This is obviously temporary, as electrons change where they are. When these temporary or induced dipoles happen, they can influence each other nonpolar molecules around them to move their electrons in a way to make an opposite charge form on the side facing the other molecule, making the induced dipole force. This force is also known as London dispersion or van der Waals forces. A big factor of how much a dipole can occur is the molecule's polarizability, or the ability of this molecule to become polar. Larger atoms or molecules tend to be more polarizable, as larger atoms or molecules tend to loosely hold onto their electrons, allowing more movement and a greater charge. These forces are weaker than that of dipole-dipole ones, so most molecules with only this type of force tend to only be liquids at very cold temperatures, where the interactions can keep molecules from separating a lot and turning into gas. I said only in the previous sentence, as molecules can have forces weaker than their primary one. So, ions and dipoles still have induced dipole forces working in them. One quick note before I end is how these usually nonpolar molecules can also be influenced by ions as well as permanent dipoles. In a way much like what happens when a temporary dipole comes close, the molecule shifts the electrons toward positive areas of charge while moving them away from negative areas to make opposite charges closer to that ion or dipole. These are ion-induced dipole and dipole-induced dipole forces respectively. To answer the question, why are some materials in the state that they are from the beginning, you could see all of these different types of forces happening between molecules. These forces have varying strengths, and these forces must either be overcome or allowed to pull the molecules together to form the states of matter that we see around us. And since they vary, material states varies as well. Thank you for watching the first and possibly only episode of this series. I hope you have learned something from it. Aside from that, I hope my pronunciations were alright, and I apologize for when my voice was a bit iffy, such as right now. And I don't apologize for those chem jokes. I hope they got a reaction out of you. Ha, get it? Pun is definitely intended there. Now, this episode was inspired by extra credits and Crash Course. Everything here is made by yours truly, and the production software will be shown below in the description. I'm Jason Chen, and as always, have a great day. and thank you.